Hello there and welcome back to the channel. Now, if you're anything like me, you've got a head full of electronics and radio project ideas, but you have trouble finding the time to bring them to life. So, between work, family, and everything in between, it feels like there's just never enough time to turn these ideas into reality, let alone make YouTube videos like these. Take this Rickroller project, for example. It was intended as a prank device that I built with my younger son to surprise our friends and family. At first glance, it looks quite straightforward. It's just a fun gadget with an infrared proximity sensor that plays Rick Astley's Never Gonna Give You Up whenever it detects an unsuspecting victim. It also has a built-in servo you can attach to an arm to knock things over, or a needle to pop balloons. So it seems simple on the surface, but to bring the project to life inside, there's an Arduino, OLED display, MP3 player module, of course buttons, power supply system, and then to add in the software, the electronics, the case design, and what seemed like a quick project turned into months of weekend tinkering. Even my work gadgets, like this contactless bank card router, or router depending on where you're from, for testing payment terminals, also uses a set of similar modules actually, Arduinos, OLED displays, buttons. And even my radio projects these days have evolved, and many use microcontrollers and again OLED displays, LCD displays, and then they kind of come in the norm. So I asked myself, how can I streamline all of this to turn time-consuming projects into more manageable builds that I can fit into my busy schedule? So today's video, I'm excited to share with you the development of a new common module, which contains all of the ingredients to satisfy most of my projects. And at the same time, I'm going to show you how I use it in conjunction with design and construction shortcuts to fast-track projects. So whether you're building projects for fun, for hobbies, or for work, I hope these ideas will help bring these projects to life faster. Now, before we jump in, I want to give a big thank you to our sponsor, PCBWay. Now, if you're into electronics like me, you know how important it is to have a good partner for PCB manufacturing. Now, PCBWay isn't just about PCB manufacturing. They also offer a full range of services from PCB prototyping and assembly to advanced options like flex PCBs, CNC machining, and even 3D printing. So whether you're looking for a small DIY project or a complex design, their high quality standards, fast turnaround times, and budget-friendly prices make them the perfect choice. They also have a community for projects where PCBWay actively supports makers and hobbyists worldwide by showcasing their incredible designs and helping them to bring them to life. So if you're ready to take your projects to the next level, head over to PCBWay.com and see how they can make your ideas reality. Check the description for the links. So the first step in designing this common module is decide what ingredients I want. So the first thing is the microcontroller. I'm going to select a Nano because they're cheap and easily available and do most of the functions that I want in projects. And if you need a bit more power, you can go to this IoT version, which has got Wi-Fi and Bluetooth, or even this STM32 version. So they've all got the same pin out, although sometimes the operating voltage of the I/O bus is a bit different. Sometimes it's 3.3 volts, so you need to be careful of that. Then the display, of course. So we have an OLED display. They're my favorite. Power efficient, multiple sizes, easy to drive. And then you need some sort of input device. So I like these Rotary encoders. They provide so much flexibility. You can have a simple or complex menu system from them. I also like to have an independent back button as well, so a few more buttons would be good. And then some LEDs to show power on status and perhaps status of some I/O, some output lines, and a buzzer to give some audio feedback. And finally, an output driver to provide high current outputs such as relays or motors or whatever it might be. So that's pretty much it. Now, those ingredients would cater for most of my projects. Not all, but most, and that's what I want. Now another time consuming thing is wiring these things up. So I want my module to be able to connect to these pre-wired wire sets. So when I say wire sets, you've got the cable and then a matching socket. Now they're available from AliExpress for just a few dollars, and they save me so much time. So it needs to incorporate these sockets so I can put in these pre-wired cable looms in. So the first thing to do is to get all of these ingredients and components into a circuit schematic. Now you can use the tool that you want, but I've used KiCad. So I've got my Arduino format microcontroller, and I've connected up all the power connections and ground connections and put labels on all of the I/O. And then I created a section for the input and output connections. So you can see here that I've got a connection for the D2 to D9 connections together with bus and power on one connector. Then I've got a miscellaneous connector with RX, TX, SDA, SCL, reset and so on. And then another one for the analog. Both have got the power connections on them as well. Now the output device I've chosen is a TBD62783, which is an 8-channel DMOS transistor array. Now the thing I like about this is that it has high side switching, which means that your load is always connected to ground rather than the positive supply. And it also has a clamp diode on each output, which protects it from back EMF from inductive devices such as relays. And here you can see the equivalent circuit, so you can see that clamp diode between output and ground, and you'd connect the load between output and ground as well, of course. Now I've got all 8 outputs of that driver going to another connector. Now you can see that in addition to those 8 outputs, I've got something called VRLY, VIN, VBus and ground. So VRLY is the supply which drives this driver, and that's selectable by J2 to be either VIN or a dedicated input, so you can have a higher voltage. Then you've got the output devices, so you've got Q1 driving the buzzer, again with a clamp diode across its output, or I could either connect a speaker to the output instead of using the buzzer and have more complex sounds using PWM if I want to. Then I've got the LEDs. I've got power LED and 2 status LEDs, one connected to D13 and the other one connected to D9. And here I've got the OLED display with its connections to SCL and SDA. Now J4 allows you to change the polarity of the VCC and ground connections, because on some displays it's horribly reversed. And then I can use J3 to select the supply voltage of a VBus or 3.3 volts. Then I've got the switches. So I've got the Rotary encoder input together with its pull-ups. And basically what you can see here is a low-pass filter which helps debounce any noise from the switch contacts. The same with the built-in encoder push switch. And the same with 2 additional push buttons which you can use as a back button or some other function. Again with the pull-ups and the low-pass filter for debouncing. Finally, I've got the power and decoupling. So each of the 3 supply rails, 3.3 volts, VBus and VIN, I've decoupled with a small capacitor for high frequency decoupling and an electrolytic for low frequency decoupling. So the next thing is the physical PCB layout. Now I tried to make it as small as possible. It's approximately 55 by 85 centimeters. And to do so, I've had to put components on both sides. Now once all the tracks have been routed, an important step is to just double check the 3D model to make sure you don't have any physical clashes between components. And also just as kind of a double check on trace alignment. It's quite easy to see if you've got clashes when kind of viewing the 3D model rather than the routing or routing layout. Now you notice that I've used a DIP or dual inline format for the output driver IC. That's because I want to put in a socket, because I'm thinking, well, if anything's going to get damaged through a short circuit or something, it would probably be that device. So I want to be able to change it out with ease. So just zooming in a bit and rotating, you get an idea of its layout. You can see that those links are for changing the polarity of the voltage to the OLED and the supply voltage, and they're placed in between the legs of the Nano just to save space. You see you've got decoupling capacitors and buzzer, and then we'll flip the board around, and then you've got the front side where you've got all the user interface type stuff, like you've got the outline for 3 possible sizes of display. So the 0.96, 1.3 and 1.5 inch display, there's the space for the encoder and buttons and the 3 LEDs. And then you can see the lines of connections for the connectors. So having checked the design, the next thing to do is to upload our Gerber files and BOM lists to our PCB manufacturer. So PCBWay make this really easy in KiCad because you have a plugin, just press on it and it does everything for you, uploads everything, and you get instant confirmation within their portal that the files have uploaded, and instantly gives you a price for some default quantities. So we've got $5 for 5 PCBs in 24 hours, and then you select the shipping of your choice, of course, and that will change the price depending on the service you want. And then you go in and basically just set up the types of parameters you want for your PCB. First of all, you set off the quantity, and then how many layers you got. It automatically detects you've got 2 layers, the type of board that you want. Also the thickness of the board, I'll leave it at 1.6. I'm going to change it to red. I fancy red boards. And what else have we got? We got the silk screen color. I'll leave that as white. The type of solder that you want, the via process, the weight of the copper on the tracks. And then you can select the assembly service. Now I don't want to do the surface mount myself, so I'm going to select assembly service. So turnkey, that's so that PCBWay supply the parts, and then I'm going to get 10 done, and I only want the surface mount. I don't mind really what components we use here. It's nothing mission critical, so I'm going to say yes, we can use alternative parts in China, and then I'm just going to put a note here that I only want PCBWay to assemble the surface mount devices for me. The idea is I'll populate the rest of the board according to my needs on the project, but I don't want to be messing around with SMD devices. Remember, the whole point of this is to speed things up for me. And that's pretty much it. Press calculate, it instantly calculates it for you, and I think $34 for 10 PCBs delivered with all the surface mount fitted is just an absolute bargain. Just amazing how that price is achieved. Save to cut. And hey presto, a week or so later, faster if you don't have the assembly, you get the delivery, and it's nicely packaged. You got something to stick on the fridge and annoy your wife. Another sticker, and then you've got a board here with nothing on it, just to show you the track layout so it's not hidden by the components fitted. Then let's have a look at the finished product. So you can see the quality is just excellent. The first banana board. So you can see, first of all, here I got the silk screen showing the outline of the 3 different displays I could fit, then 0.96, 1.3 and 1.5. It's important to have that outline source, of course, so you don't have any clashes. This is where we're going to put the rotary encoder, and then the 2 push buttons, 3 LEDs, a power LED and 2 status LEDs, and the connectors. You can see that I've marked the silk screen showing the connections, and I've got that on both sides. I'll show you why later. And there's the output, the high current outputs, and that's where the power input connector is. And then that's the OLED connections in the middle of the display. And then here I've got the links to select what input voltage goes to the output driver IC, where it's V in or an external power input. Then on the rear of the PCB, things get quite busy. So first of all, you can see the SND devices and the buzzer. So all those devices being pre-assembled is going to save me a lot of time. And then we have all of the connectors. So this one is for the analog connections, and then we got miscellaneous and D2 and D9 and the high current outputs. We've also got the decoupling capacitors, and then we've got, you can see, a place for the nano and the output driver IC. Now the idea is I'd only populate these boards with components as necessary depending on the project or application I'm using it for. This board is fully populated, and I just want to show you how I can accommodate different sizes of display into the same design. So here is the 0.96 inch display, the smallest that I use. And then here is the next size up, which is 1.3 inch. And finally, the 1.5 inch. So this is nice, so I could use the same board for 3 different types of display, depending on the project's needs. Of course, I've got the Rotary encoder fitted, and push buttons, power LED and 2 status LEDs. And then on the other side, you can see I've fitted everything, all the connectors. Let me just show you where the nano goes. So we just fit the STM32 base nano. Let's see how it goes. You can see underneath it is the links to set the polarity of the display, and also the display voltage. Again, that's the safe space to put it in between those legs. Now, let me just show you something. You can see here on this 0.96 inch display, you've got ground on pin 1, VDD on pin 2. But on this 1.3, sneakily it's been reversed. And then on the 1.5, it's the same as the 0.96. The SDA and clock connections are the same. So that's why I put in these links, so that I can change the polarity or the voltage. So here's the output driver IC. You can see that's in a socket in case I blow it up. The decoupling capacitors and all of the connectors, which will connect with the pre-made cable looms that I can buy off AliExpress. And here's the link to select the input voltage to the output driver and the buzzer. So that's pretty much it. Now, what I want to show you next is a board that I've populated specially for prototyping. So what I've done is I put the connections on the front side of the board. Of course, normally they go on the reverse. And I've used these pins so that I can connect standard, like DuPont links into a breadboard. I've got my output driver socket, and that I just fitted in this case as a standard nano. So you see all of the connections are accessible on the front with those pins to make it easy to make connections to breadboard for prototyping. And then I've developed this 3D printed case, and that connects to the power socket on the banana board and presents those power connections at the 4mm jacks at the back. And the case doesn't require any screws, it just snaps in place like that, so I can quickly test boards before I put them into a project using this case as well, so it's completely screwless. So there's the connections for all of the power rails, again for easy prototyping. So we just connect the power connections to the banana board and we just snap it in place. he says, let me just put it in properly, there. Okay. And then of course I can easily test displays with this as well, because I've got the socket on the top, and it's just easy to pop in different displays and just check they're functioning correctly. So again, a time-saving idea to reduce time from prototyping to a working project. And because I've put all the links on the top side of the board, I can easily change the polarity to adjust it for different types of OLED display as well, without having to remove the board. So it's all configured for quick prototyping, quick testing. And there you go. So what I'll do now is I'll just demonstrate how easy it is to connect to a breadboard. So here you can see I've got it positioned in front of the breadboard, and then I can just make the links across. In this case, in case you're interested and you know something about radio, I'm actually connecting it to a SI4732 radio IC, DSP radio IC, and I'm using it to experiment with a feature called soft muting, which is something that happens when you tune a DSP radio. I'm using software from an off-the-shelf radio, an ATS20 Plus, and providing all the relevant chips and infrastructure so that the software runs on a breadboard. So I've got basically this chip connected using SLA and SLD, and an amplifier chip for the audio output connected to a speaker, and that pretty much provides a radio, and really quick to implement using this system. So what about software? Software takes time as well, doesn't it? So what I've done here is I've created what I call base code for this board. So it obviously defines all the inputs and outputs for this particular board, and also provides the basic structure for a menu system using the Rotary encoder and functions to sound the buzzer and so on. So using this base code, then I can expand it to cater for specific functions. And I can use ChatGPT, so I'll put this into ChatGPT and I will say to it, using this code, implement this. So in that way I can implement code really, really quickly for this board. Then also the 3D modeling. So I created a model of this board, and I've actually got a model for each size of the display. This one is for the largest display, the 1.5 inch, which you can see here, and showing the position of where the data connector is for uploading software. And then I've created another model of it, which extends out all the components that I need to make a whole in the panel in which it's going to be fitted, such as the LEDs and the display. And then I can use that to subtract from a panel to make the holes in the right places. So you can see here that I bring the model into a panel, and that can be an enclosure or a box. I just shown a flat panel to make it simple. And then I subtract that model from the panel or enclosure to provide the openings in the enclosure in precisely the correct locations every time. So that makes it, from a construction mechanical point of view, really quick to implement. Now, as I was about to conclude this video, our hot and cold water dispenser broke down, and I was going to get it repaired, and it was charged like it's going to be over $500 to get it repaired. So I had a look at it, and so it turns out that the microcontroller had failed. So I thought, well, what a brilliant opportunity to test out my new banana board and see how quickly I can provide a solution to repair the water dispenser with. The first problem I had, I didn't have any information about the built-in cold temperature sensor, so I had to replace it with a DS18B20 temperature sensor, which I got off AliExpress. So then I cut away the insulation from under the cold water tank and temporarily put the sensor underneath the tank, like so. Excuse the tape, it is only temporary. And then I connected that to the Banana board in its prototype case, and with the connections on the front, I managed to connect that to the interfaces of the existing microcontroller, so I could control things like the output relays and things like that, switch on the chiller and water dispenser. And then I left it running like that with some software which I got ChatGPT to help me with, and left it running. And then I took a Banana board and I just populated it with the parts I needed just for this project. So you can see that many of the components are missing, many of the connectors are missing. I just populated it as needed. See, I have just a one decoupling capacitor, one connector, buzzer, and of course the SMD connections are already there. Sorry, components are already there. So once again, really quick to put together. For the controller, I only need a basic Nano for this, so I had a couple of basic ones lying around, so I've used one of those, and that's pretty much it. For the case, I put together a basic case which would fit the contours of the water dispenser, and I used the 3D model of the Banana board to ensure that the cutouts in that case were in the right place and to make sure everything fits together properly. And here's the result, 3D printed, of course. And what you'll notice here is the openings for the LEDs are rectangle rather than the usual round, and that's so that it fits in with the style of the other LEDs. And of course, got openings for the buttons and the rotary encoder and display. I fitted brass screw inserts to secure the Banana board. And then I used clear PLA to produce some buttons. Let's show you how these fit in. So of course these go in between the push buttons on the Banana board and the case. And I thought, well, it seems they're from clear PLA. It would be great if I could make them illuminated, and I could connect that to the LEDs, the data outputs of, or the spare I/O outputs on the Banana board. So you can see here I've changed the design a bit so I can put a 5mm LED in the button. It works surprisingly well, actually, as I'll show you later. And there you go. And then I made some diffusers out of the PLA, the clear PLA, which is a rectangle shape to fit into those rectangular slots. Oops, a bit fiddly. There we go, just pop them in. There, it gives me the look I was after. So then the next job was to wire it all up and check that the Banana board still fits in after everything's wired together. And that lines up perfectly. Then finally screw it all together. You can see at the bottom there the interface for the temperature sensor, which I've glued into place. And check the buttons operate properly. And then use the pre-wired connectors that I bought from AliExpress to connect everything up. Again, to save me time. And finally tidy up the wiring, make a hole in the water dispenser for the cables, and then put it all together. And there you have it. And the good thing about this, it actually adds new features it didn't have before, such as you can dispense a predetermined volume of water to fill a cup or a glass. And then a long press shows you the temperature of the water over time. So that's it. Thank you for watching, and I hope that there were some ideas or techniques which were useful to you and perhaps you can incorporate to save you time on your projects. Now, in case you're interested in using the Banana board yourself, I will put links in the description such that you can go to the PCBWay website and order copies of the board yourself. Again, populated with SND components. And I will provide information and links on the prototyping case and of course the circuit schematic and the default code. It won't be available immediately, but certainly in the next few days I will upload it. So by the time you watch this video, it will probably already be in the description. Well, I hope it was useful to you. Thank you very much for watching, and take care and look after each other. Until next time, bye-bye.